Now we will discuss about the microfabrication techniques which are being used for developing micro robotic system, which is a part of this particular module. Ideally, the main focus of this particular module is to expose the participants towards the different microfabrication techniques which are being employed for developing any kind of micro systems or micro devices, or to develop certain amount of mechanisms which has a direct relevance towards microfabrication related applications. Now, if we try to overall look into the microfabrication techniques, which so this is how basically a fabrication process is being deployed. So there are 4 basic microfabrication techniques which exhibits. So this is a kind of a flow which is being deployed over here. So in this particular flow, let us consider this is a kind of a sample which is being used. So within this sample, so there is a kind of a thin film deposition which exhibits, followed by either a photolithography in case if we are working in a domain which is less than the few microns, or in certain cases we do not use a photolithography, we will directly go for a kind of a wider spectrum where we are working in the range of 1 micrometer, etc. Then we have a process called etching. So in between there is also a process called doping. So the main function of this doping is to improve certain functionalities which includes a kind of a charging capability or a kind of an electrical capability, etc., are being taken care by this doping process. And then there is a mass process which exhibits over here, and finally we get a product coming out of it. So this is a kind of a generalized process flowchart or process map which is being established for developing different microsystems or microsensors, etc. However, in order to classify the type of microfabrication process, or in order to introduce you to the different components which exhibits towards the microfabrication, or which exhibits towards developing a kind of a microsystem, the first component which exhibits is the substrate. So substrate is a kind of a freestanding layer. So over this freestanding layer we try to build the structure what we are looking for. For instance, like a substrate can be a kind of, either it can be a glass, or it's a kind of a quality of material, or basically it is more towards a material specific. So when we try to talk about a substrate, so the substrate can be either a silicon wafer, in certain cases it can be a glass. If we are more focusing towards a kind of an optical functionality, quartz can also be used. In addition to this, there are different flexible substrates are also available. So the main function of these flexible substrates are, so we have an active medium. So in order to cater the active medium, or in order to participate along with the active medium, such kind of flexible substrates can be deployed. Or these flexible substrates, sometimes they are transparent enough in such a way that we can see the complete functionality of the device what we are fabricating. Now when we try to look into the substrate selection, so the substrate is basically selected based on the quality of the material, based on the functionality of the device, and based on the material specific. So this substrate acts as a base. Over the base normally materials are deposited. So in certain cases, for example, if you are talking about a smart material, so these smart materials can be efficiently deposited on a substrate, and by actuating it appropriately we can have a certain functionality. Let me just give you a simple example. We are working on this concept called SMA biomorph. So in the case of SMA biomorph, we have a shape memory alloy which is being deposited on a polyimide layer. So these polyimide layer are programmed in such a way that it has a well adaptability with the SMA. So when an SMA gets actuated in this particular direction, or with a particular displacement, this polyamide will also try to take the same shape. That is, when we try to actuate this shape memory alloy, so there will be a kind of a deflection which exhibits over here, and when we try to cut off the actuation, it comes back to its shape. So here in this particular case, the substrate is participating with the actuator for our applications. Okay. So here this is a kind of a flexible substrate which exhibits. In other words, we can also have this substrate a kind of a supporting structure. So over the substrate we can build a layer, and then we can etch this substrate so that this active layer can be efficiently used for actuation as well as for different micro robotic or microsystem application. So ideally this deposited layer is considered to be an active layer which participate into the system. Now if I need to create certain amount of features on this deposited layer, so we may need to have a kind of a masking which exhibits over here. So these masks are placed, and then we are trying to expose these layers to a kind of a light or a certain amount of like either it might be a laser or it might be a kind of a mechanical machining where these deposited layers can be efficiently removed. So ideally what happens is, if I want to create a feature like this, so a mask is which was placed over here will protect the particular deposited layer which was below this particular mask, and then we get the final features what we are looking for. Now ideally if you see in this a particular overall flow, so there are two important technical parameters which are being emphasized over here. One is called as a additive process, another one is called as a subtractive process. So as far as in this additive process is concerned, so we are trying to add up the material. In this kind of subtractive process is concerned, so we are trying to remove the material. Okay. So this is how. So overall if you try to look into the microfabrication process, so these microfabrication process can be classified, that is for MEMS or micro robotic applications can be classified into two. One is called as a bottom up approach, the other one we call it as a top down approach. So what is this bottom up approach and top down approach? So before going into this, so we have to understand the overall functionality of the substrate what we are using. So one of the key substrate which exhibits is a kind of a silicon wafer. So this is the overall photograph of a silicon wafer which is used for growing certain amount of layers. Okay. So the overall functionality of the growth basically depends upon the thickness of the silicon wafer. It also depends upon the size and shape of the structure with the different applications. It also depends upon the purity of the material what we are considering. So it also depends upon the overall surface quality of the substrate. Like for instance, suppose we are designing a micro robot for a kind of underwater application. It is expected that it should have a kind of a hydrophobic capability. Okay, so that the water doesn't stick onto the surface. In certain cases, we may need to have a kind of a robot, micro robots, which is used for which has a kind of a hydrophilic capability. So here the surface quality play a vital role. So wherever I need to have a kind of a structured pattern, so in those structured pattern, so based on the functionality or based on the characteristics, I can generate such kind of, or I can have an impact on the surface quality based on the requirement or based on the characteristics. So the most important point which we may need to consider here is the microfabrication should go in hand in glove with the substrate property which has a direct impact towards the functionality of the system. Now, let us discuss about the overall classification of this microfabrication. Of the microfabrication So, ideally a microfabrication process is classified into two. One is called as a top down approach and the other one is called as a bottom up approach. That is, let us consider we have a substrate. Over the substrate, if I need to build a structure like this, let us consider I am looking for, I am in the verge of developing a actuator. This is a kind of a comb drive actuator. This is a part of a comb drive actuator. So, I have two different options. One option is with reference to the substrate, I can build layer by layer. So, in order to build this layer by layer formation, I need to create, I need to have an appropriate masking over here. This masking will take care of the feature generations. Okay. So, that is like when we are trying to build these structures. So, let us have a kind of a targeted material and this is a kind of a substrate material. Through this targeted material, we are trying to throw the particle on the substrate. So, when we are trying to throw the particle on the substrate, so what happens is the particle will try to get aligned or it will try to build, and wherever the particle deposition is required, so that particular domain is taken into consideration. Wherever the particle is not required, so we have a masking in place. So, by leaving the masking, so appropriately we try to build the structure. So, this is called as a bottom up approach, that is from the bottom we are trying to build the structure. Next, when we try to talk about a top down approach, let us consider I have a bulk layer. So, that is the substrate, and over the substrate we have a bulk layer, and what we are trying to do is using an etching process again we create a mask over here. By exposure to light or by exposure to through a laser or sometime by exposure through chemical means, we can etch these layers, finally ending up in such kind of high aspect ratio features. Okay. This process is called as a top down approach. So, a top down approach we can also mention it as a kind of a subtractive approach. Bottom up approach can also be called as a additive approach. There are wide varieties of techniques which are available for this top-down approach as well as for this bottom-up approach. So, as far as this top-down approaches are concerned, as far as in the case of thin film technology, like we have this we have lasers which are being efficiently used for etching applications. We can also consider a kind of electron beam lithography or electron beam based etching, which can be used for efficient etching applications. We can also go for certain amount of chemical treatment which are being effectively used for etching such kind of features. So, in all these cases, either we use a mask, or in certain cases we try to focus the energy which we are using it, so that these energies can be efficiently used for etching related applications. However, when we try to talk about an additive approach, so in the case of an additive approach, so what we try to do is we try to build layer by layer. So, for this layer by layer processing, there are different types of techniques which are available, which, like, if we try to classify these techniques, these techniques are classified into two. One is called as a physical vapor deposition technique, and the other one is called as a chemical vapor deposition technique. So, as far as in this physical vapor deposition technique is concerned, so what we try to do is, so we convert a material in the form of a vapor, and these vapors are being efficiently get deposited on the surface. So, let us see what is the physical vapor deposition technique is concerned. So, this is a sputtering process which comes under the category of the physical vapor deposition. So, as far as in this physical vapor deposition is concerned, so there is no reaction here, rather a material is physically transferred to the substrate through various processes such as flash evaporation or e-beam process or a RF sputtering. So, like here, if you look into the overall materials, so we have metals and ceramics which are being efficiently used, and the primary feedstock for such kind of physical vapor deposition are either it might be a wire, or it might be a powder, or it might be a pellet. So, primarily if we try to look into this physical vapor deposition, so these physical vapor depositions happens inside a vacuum chamber. So, there are different types of physical vapor deposition is there. One of the preliminary physical vapor deposition is a kind of a thermal evaporation. So, as far as in this thermal evaporation is concerned, so when I try to introduce you to the different components of a thermal evaporation, here we try to keep the substrate, and this is a kind of a source material. So, as we have discussed before, the source material can be the source material which can be efficiently deposited using this technique will be a metal, and these metal will be placed inside a kind of a tungsten boat which exhibits over here, and the tungsten boat basically what does is it tries to heat the material, and the material takes a kind of a vapor phase, and these vapor phase will try to deposit it on the substrate. So, what happens is when the vapor gets deposited on the substrate, so there is a kind of a bottom up approach which exhibits, and owing to this bottom up approach, so you try to get a thin film or a thin layer which persists over here, and based on this thin layer you can see a kind of a structure which is being established. So, if you try to look into the overall characteristics of it, so almost a working of the bulb, it is almost a kind of a similar phenomenon. So, where we have a kind of a filament, we try to heat the filament, the glow discharge from the filament is being seen as a kind of a like a kind of a glowing discharge which is being exhibited over here. Similarly, one of the other example of a sputtering process is other methodology of a PVD process is a sputtering process. This sputtering process is slightly different from the earlier thermal evaporation techniques. Here the process of deposition is not thermal, but it is through plasma. So, that is, so what we have is, so we have a vacuum chamber in place, then there is a sputtering gas which is made to flow into it. We have a thin film which is being kept over here, and then there is a sputtering target which is available. So what happens is through this sputtering gas, so we try to, so this is the material which needs to be deposited on the substrate. So let us consider, so I need to sputter a kind of a, so we are developing a kind of a shape memory alloy based micro robots, where we are trying to develop a kind of a, we are taking a nickel titanium as our target, and this nickel titanium is being sputtered by applying a kind of a potential to it, and by applying this potential we get a kind of such kind of plasma which is being exerted over here, and this plasma is made to sputter on the surface in the form of a thin film, and this thin film will result in a deposition. So here in this particular case, like this sputtering process is classified into two. So one is called as a DC sputtering, and the other one is called as a RF sputtering. So as far as DC sputtering is concerned, it is mainly meant for metals. As far as RF sputtering is concerned, it is mainly meant for oxides. In fact, the typical sputtering phenomenon is almost kind of a CFL bulb, where plasma is used as a kind of a process. Now when we try to look into the CVD process is concerned, so in the case of a CVD process, where there is no kind of a physical we are not trying to melt the material, where it is more to do with a kind of a chemical reaction which exhibits over here. So in the case of a CVD process, so we have a substrate in place which is being kept over here, and then a gas precursor is made to pass through this particular vacuum region. So when the gas precursor is made to pass through this vacuum precursor, so what happens is there is going to be a kind of a certain chemical reaction which exhibits over here. For example, so if we are trying to develop some kind of zinc oxide based structures, so what we try to do is we try to keep a boat. Over the boat, we try to keep a zinc oxide plus graphene. These graphene will act as a catalyst along with the zinc oxide. The area where it needs to be coated with zinc oxide, so will be placed over this board, and the gas precursor inlet will be made to pass through this. So when the gas inlet is made to pass through it, it reacts with zinc oxide and graphene, thus leading to a kind of a evaporation which exhibits over here, and this evaporation will result in a grind of a growth of the film. So wherever we are working on a high temperature materials such as silicon carbide, etc., such kind of CVD process can be efficiently used. However, one of the major limitation of this CVD process is masking, because masking the CVD process is quietly difficult. However, in the case of a PVD process, like it is possible to do a masking appropriately to create a certain structure or the certain parameters based on our requirement or the characteristics what we are looking for. So that is one advantage of using this. So that is one advantage of going for a PVD process, whereas in certain amount of high temperature applications we normally prefer to go for a CVD process. So ideally, like in the overall, if we try to look into the overall additive processing, that is a bottom up approach, these two processes are taking a major share in building up a certain amount of structures for our applications or for different micro robotic systems.
Shape memory alloy based thin film micro actuators can be fabricated using physical vapor deposition techniques. So in physical vapor deposition techniques, we are basically creating physical vapors of the material that are being deposited on a substrate. The techniques that we will be discussing here are thermal evaporation and electron beam evaporation. So this is our machine for thermal evaporation. So its basic principle is Joule heating. So in Joule heating, what we are basically doing is we are simply heating the material which will be getting melted and evaporated, and then getting transferred to the substrate material. Substrate material that we are using for fabrication of flexible micro actuator, it is Kapton polyimide. So why we are using Kapton polyimide? Because it is a flexible as well as it can withstand very high temperature of 500 degrees Celsius without being degraded, so that it can cater to our high temperature actuation needs. We can use these Kapton polyamide in two different forms for substrate material. One is in a sheet form, which you can see here in this substrate holder, and another one it is in belt form. So that depends on how much pre-staining we want to do in our material. So this is basically for training of our material, training of shape memory alloy based thin film. So because in thin film we can't do training post deposition. So that is why we are doing pre-staining in substrate itself. These substrates, they can be deposited with the nickel titanium or nickel titanium copper based shape memory alloy thin films using tungsten boards that you can see here. This is our tungsten board in which the material is being fed, whether in let's say powder form or pellet form or wire form. So currently we are using it in wire form in current deposition. So this is the basic chamber inside of the thermal evaporation unit. So we will be putting our material here on the top. This is our substrate material which is going on the top, and at the bottom in the tungsten board we will be putting substrate. We will be putting our source material which is nickel titanium, let's say for current case, and that this tungsten board, it is being heated with the help of two copper electrodes which are being supplied very high power up to being red hot, which melts and evaporates the material. Also, the deposition process is being done in a closed evacuated chamber at a very high vacuum of around 5 into 10 raised to minus 5 millibar. So this high vacuum, it is being created using two different kinds of pumps, which is rotary and diffusion pumps. Post deposition, our film will be deposited on a Kapton polyamide substrate, and it will look like silverish color or NIDI of film. This structure is a double layer structure where nickel titanium, it is being deposited on Kapton polyamide substrate, and we term it as bimorph. Why? Because it has two active materials. One is Kapton polyamide and another one is nickel titanium, both taking part in actuation cycles, one in cooling cycle and another one in heating cycle. The second process for shape memory alloy based micro-actuator fabrication using physical vapor deposition is electron beam deposition. So this is the unit for electron beam deposition. The basic principle for e-beam deposition or electron beam deposition is generation of an electron beam, high energy electron beam, that will hit our material and melt and evaporate it. So how we generate it? It is basically done using a tungsten coil. So here you can see at the bottom there is a tungsten coil, and when we supply very high power to that tungsten coil, it will generate an electron beam by virtue of thermionic emission, and that electron beam, it will come directly out. So we turn it by 270 degree using a magnet that is just behind the coil itself. So as my electron beam will go into that crucible by bending through 270 degree angles, it will hit my material, which is a source material, that can be nickel titanium or nickel titanium copper, or any other shape memory alloy that I want to coat, and as it reaches the melting temperature and evaporation temperature of the source material, my material will evaporate and it will deposit on the substrate, that can be in sheet form or a belt form that we have discussed in previous thing also. So this is the Kapton polyamide substrate in the sheet form. So we'll put it here, just we'll hang it right above the crucible here, and here my crucible is placed. So as the electron beam will come to hit the material in the crucible, which is of graphite material, and here my material will get evaporated and get deposited on the sheet itself, and then I will get bilayer structure, which is a bimorph structure for actuator fabrication. So different kinds of actuators can be fabricated using this flexible structure, and we can have customized structure also by using laser micro machining also, which we'll discuss further. So this is my tungsten crucible, where we'll put our source material, which is nickel, titanium, or any other shape memory alloy for the deposition on the substrate, and we'll place it just above the tungsten coil, where the electron beam will hit, and melting and evaporation of the source material will happen for deposition. Since we are using the electron beam for directly hitting the material, there is no indirect heating. It is direct heating of the source material. So in this case, the great advantage is we can melt and deposit very high melting point materials.
So the flexible micro actuators, after the deposition, they are fabricated using laser energy with fiber laser. So why we are using it? Because we want to make flexible actuators of customized size. So generally, for thin films, laser energy is very high energy thing for machining. So it either burns the film or either it creates the damage to the film. So with fiber laser, the energy and the direction of the laser, it can be easily controlled to get the customized shapes. So the better point in this is we have a galvo here. So that galvo, it controls the position position of the laser beam which is coming through, and it is always in focus position itself. So the basic thing in fiber laser is it has a fiber laser source, an optical fiber, so which is a lasing source. So it is being pumped through a diode laser, and it amplifies the diode signal to produce a laser beam, which then reaches the galvo head, where we can move it with the help of moving coil mechanism. So there is a moving coil inside it, a magnetic coil, which will move according to the input given with through the software. So we can directly put whatever structure we want in the software, and that can be directly replicated in the laser motion here on the platform itself, and that way we can get the desired shape and size of the is any of the actuators that we want. So different kinds of actuators we have fabricated using this fiber laser, which are the circular or triangular or rectangular as well. And one other application that we have used it for, it is this optical shutter. So for optical shutter also it has been used. In the next part, we will see how directly we are using the laser energy for fabricating these different structures, let's say for triangular actuators or this optical shutter actuators. So the Wymore-based flexible actuators, they are tested for electrical actuation using the customized test bed, which is shown here. So in this, we supply electrical power in frequencies, in different frequencies at different powers, so that it actuates for a number of cycles up to the failure of the Wymore structure. So the basic circuit, it consists of these following components. First is our power supply, which will directly connect to the control circuit to our Wymore structure. And the control circuit consists of these two components, where we have Arduino and relay, which is used to change the frequency of the supply power, so that we can have different kinds of motion for the Wymore structure. As we supply the power, the Wymore will actuate in the forward direction, and that actuation is captured with the help of a laser displacement sensor. And that input to the laser displacement sensor, it is recorded using a data acquisition system or DAC unit, which will convert this laser displacement data into a recordable data we can be displayed on a lab with software in graphical form. Then that graphical form can be used for further studies. So this setup is used for study of bimorph for electrical actuation for a number of cycles. Let's say we use it for 1 lakh to 2 lakh cycles up to the failure where either the thin film which we have deposited, it will get delaminated, or we are getting a burning of the film. So in that case, actuation of the film stops, and there we can say we have studied the life cycle of the biomorph structure.
So the shape memory allows thin film biomorph that we have fabricated using different physical vapor deposition techniques such as thermal evaporation or electron beam evaporation that we can use in various applications such as Stuart platform assembly that we are going to show here. So firstly, what we do is we cut different structures such as circle or triangular structure with the help of laser energy with laser micro machining, as we have also discussed previously. So the same structures we use for fabrication of Stuart platform assembly. So this Stuart platform assembly is basically what we have learned in different studies also. Like the base is a fixed base on which we have a moving platform, which in our case is a mirror, which is a lightweight mirror, which is in the central part. As you can see here, this is our central part, which is the movable platform or the mirror. And that mirror, it is supported using four different actuators. So all the parts are NITI SMA based, and they have been micro machined using laser energy of the fiber mirror. And then this structure, in this structure, the mirror, it is being moved with the help of the motion of these four actuators individually or in combination. So when we supply energy, electrical energy to any one of the actuator, it will actuate in forward direction, as we have seen in electrical actuation video also, that when we apply the energy, the actuator will move in the forward direction, and because of that forward motion, our mirror will tilt in upward direction or downward direction according to the motion of the actuator beneath it. And because of that motion, our mirror tilting will be there, and that mirror tilting we will be using for further application of laser beam steering for, let's say, optical scanning or optical communication applications. So the first thing here is you can see there are Arco markers. So these Arco markers are basically used for position detection of the mirror, so that we can accurately determine at what position or what angle our mirror is currently at. So we have put, for simplification, we have put 3 different Arco markers at different positions of the mirror. And initially at horizontal position, what happens, there is a camera on the top. As you can see here, there is a camera on the top. So that camera continuously monitors the position of the Arco markers. So initially our mirror is at horizontal position, and in that position the camera, it takes the position of these 3 Arco markers, generate the equation of a plane which corresponds to the horizontal position of the mirror. And as we supply power to any one of the actuators, this mirror will actuate, this mirror will tilt, and because of that tilting, the position of the Arco markers with respect to our camera, it will change. And as it changes, the new position will be detected by the camera, and it will again generate an equation of new plane and will give the final angles of the plane or the mirror with respect to the initial position. So like here you can see in this part, so when our mirror is moving, the x and y positions are changing. So these red, blue and green lines, they are the x, y and z axis of the Arco markers, and as our mirror is moving, these positions are also changing and our angles are changing here. So we can get a live feed of what our angles are and what is the position of mirror is, and the same we can use as a feedback to control the input power of, to the actuator, so that we can control the final position of the mirror, and as a result we can control the final position of our laser beam or optical beam to the point where we want to position it. Or let's say if we want to scan a whole area by cyclically moving the optical beam, then we can provide the power to any one or more of the actuators continuously in cyclic form, so that our mirror will move in a to and fro motion. It will tilt upwards in one cycle and then come back in another, so that we can have a raster scanning kind of pattern for the whole scanning of the area. Also, these arco markers, they can be used in another applications such as for position detections of any moving object also.